Well, hello there, superstars. I've got our review, no preview video for this week. We're going to look at all the facets of implicit differentiation, basic implicit differentiation, which is really not that basic, and then both derivatives of the natural log and logarithmic differentiation. So remember, implicit differentiation is nice when we have implicit relations, which are not in the form y equals something in terms of x. It's great because we're able to take the derivative of each term as it comes, but sometimes we have to remember some of our old derivative rules. For example, in this example, I'm going to be taking the derivative of a trig function, so I need to remember that derivative. Anytime I take the derivative of something involving y, I multiply by y prime. I also need to be ready to use the product rule when I have two functions being multiplied. And I need to remember that the derivative of a constant is equal to 0. So let's go ahead and start on this one. First, this tangent is a chain rule function, the outside function being the tangent and the inside being y. The derivative of tangent is secant squared. What starts in parentheses stays in parentheses. And the derivative of y is 1 times y prime or y prime. So that final derivative would be y prime times the secant squared of y. Plus, here I've got a product rule. So I'll have u as 5x and v prime as y squared. The derivative of 5x is 5. The derivative of y squared is 2y times y prime. So that gives me 5y squared plus 10, don't forget to multiply those coefficients together, xy, y prime. And on the other side, the derivative of 10 is 0, so I will set that equal to 0. Now from here, I need to isolate my y primes so I can factor. So I'm going to need to move this 5y squared to the other side, which will give me y prime secant squared of y plus 10xy y prime equals negative 5y squared. Now I can factor out that y prime, which leaves me with secant squared of y plus 10xy equals negative 5y squared. And then I'll divide both sides by that quantity to get my final answer, which would be y prime is equal to negative 5y squared divided by the secant squared of y plus 10xy. So that's an example of kind of run-of-the-mill implicit differentiation. Let's look at the derivative of natural log next. So let's start with the fun fact up at the top, which is the derivative of the natural log of x is 1 over x. And we can utilize that in a lot of different situations. Oftentimes there's going to be the chain rule embedded in problems like this. So let's look at a couple. Let's say first that we have y equals the natural log of 3x. Now, this is a chain rule function, the outside function being the natural log, the inside being 3x. So taking the derivative of each of those, derivative of natural log is 1 over what started in parentheses, which is 3x. The derivative of 3x is 3. So our final answer comes from multiplying those two things together and simplifying when applicable. So our final derivative would be 1 over x. Now let's look at a similar example. Let's say this time we have a coefficient out front. So it's still going to be a two-level chain rule, remembering that a coefficient is never a level in itself. So that coefficient will just be part of the outside function. The derivative of the outside will be 5 over what started in parentheses, so that's x squared. The derivative of x squared is 2x. So our final answer is 2x over 1 times 5 over x squared. That would be 10x over x squared. And because there is at least one x in both the numerator and denominator, we can take 1 away from each for our final answer, which is 10 over x. Now, finally, let's look at an example that has more than one of these terms. So let's say we have y equals 3 natural log of x to the 4th minus 5 natural log of 2x. Now, there are multiple ways to look at this. Whether you were to use your properties of logs to combine them, you can do that, or you can just take the derivative of each term and then combine those as you are able. So I'm going to take the second approach. I'm going to take the derivative of each of these separately. So the derivative of 3 natural log is 3 over what starts in parentheses. The derivative of x to the fourth is 4x cubed. So the derivative of that altogether would be 4x cubed over 1 times 3 over x to the fourth, and that would simplify to 12 over x. Okay, so y prime equals 12 over x minus, because of this minus right here, 5 natural log 2x, another chain rule. 5 natural log, the derivative of which is 5 over that original value. The derivative of 2x being 2. So I take 5 over x times 2 over 1, which would give me, 5 over 2x times 2 over 1, which would be 10 over 2x and would simplify to 5 over x. Now, my final answer, I've got 12 over x minus 5 over x. Now, if you left it like that, that's okay, but because they have a common denominator, we can simplify to 7 over x. Right, which would be awesome if you had that for your final answer. And finally, we're going to look at some logarithmic differentiation. And the idea behind this is we use the properties of logs to bring the power down when the power is in a variable, because otherwise it's kind of untouchable. We can't use the power rule because it's not a power function, it's an exponential function. So when we have logarithmic differentiation, we know we need to use that if we have the power as a variable. So what we can do to start is just use our properties of logs to use that power pack punch, which brings the exponent down and out front. So notice so far all we've done is some algebra. So from there, we're going to take the derivative. The derivative of the natural log of y is 1 over y times y prime. Now right here, x times the natural log of 5, this is just some number. It's a yucky decimal, but it's a number all the same. And the derivative of a number times x is just the number, the natural log of 5. To simplify, or finish, I should say, we'll multiply both sides by y. And then finally, since we know that y is equal to 5 to the power of x, we will substitute that into our final answer, okay, for our final derivative. Let's look at one more. So here's a slightly more complicated version of logarithmic differentiation where we have two things being multiplied. We have the variable as an exponent, so we're going to need to use our logarithmic differentiation. So I start by taking the natural log of both sides. Now from there, I can use my property of logs to separate those and bring the powers down. So I'm still just doing algebra. I'd have the natural log of 5 plus 3x natural log of e plus x natural log of 7. Now there's quite a few things that simplify in here, so let's talk through that. Right here, the natural log of e is 1, and that is because the exponent on e, when it's just by itself, is 1, and that's what the log is asking for, so this whole thing equals 1. And I guess the next piece we'll see when we start to take the derivative. So I can really get rid of that and just leave the 3x there. So now I'm going to start taking the derivative. The derivative of the natural log of y is 1 over y times y prime. Now, the derivative of the natural log of 5, that is just a constant. So the derivative of that equals 0, and so that's not going to do anything down there. I'll just leave it. The derivative of 3x is 3. And the derivative of x natural log 7 is some number times x, and the derivative of a number times x, since the derivative is the slope, is just the number, the natural log of 7. I can then multiply both sides by y using my parentheses carefully. And then my final step will be to put that original function back in place of y. And I've got my final answer. Thanks for listening, superstars.